The last speaker of today is actually Montanaro from Bristol, and he'll talk about a complexity classification of local Hamiltonian problems. Please, right.
Yes, so good afternoon everyone, and before I start I should thank the organisers, and in particular Steve, for inviting me along to this. It's very nice to be here, and it's particularly nice to be scheduled in the same session as the previous talk, because somehow they're kind of very complementary to each other, because somehow the previous talk was the good news about the local Hamiltonian problem, and this talk is pretty much the bad news about this problem. So, last time we heard about some nice cases where we can solve this problem efficiently, even with a classical computer. And now I want to talk about a number of other cases where we think that we can't solve the problem efficiently, even with a quantum computer. So everything I'm going to talk about today is joint work with Toby Cubitt, who's there and in the audience, and to whom all questions about the physics behind this should be addressed. And everything I say is in this paper, which is on the archive as of a few days ago. Okay, and please do ask questions at any point during the talk, especially if I say something that's kind of unclear or confusing about the model, or indeed anything else. Okay, so yeah, let's get started. Let's try and get started. Okay, great. So I'm going to start out by taking a perspective kind of from computer science and talking about constraint satisfaction problems, which are this kind of very interesting and fundamental class of problems that have been studied really since the early days of complexity theory. And yeah, later on I'm going to sort of see how these relate to quantum information. But first I'm going to start with something that's purely classical, which is constraint satisfaction. And I'm going to kind of briefly mention a couple of problems which are interesting in terms of their contrasting complexities. So the first is this problem called 3-sat, which many of you are probably familiar with. So we're given a Boolean formula, so something like this, something involving ands, ors, and nots, in so-called conjunctive normal form. So it's a bunch of clauses containing ors separated by ands. And it has at most 3 variables in each of the clauses. And we want to see whether there's a satisfying assignment to the formula. So that's an assignment to all the variables so that the formula evaluates to true, or to 1, if you like. It's well known that this problem is NP complete, so it's considered very unlikely that there's an efficient classical algorithm to solve it. On the other hand, there's a somewhat similar looking problem which turns out to be quite different, which is the problem of solving linear equations over F2 with 3 variables per equation. So here the idea is that we have a system of equations, and each equation contains some variables which are over F2, so they're like 0 or 1. And we want to know if all of the equations can be satisfied simultaneously. So here we have a few of these equations, and it turns out that this can be solved efficiently in polynomial time by using Gaussian elimination. So the first of these 2 problems is NP complete. The second one's in class P, so there's a polynomial time algorithm for it. This kind of illustrates these sorts of problems can have very different complexities, despite superficially appearing very kind of similar. And in fact, these are just 2 possible constraint satisfaction problems from a much broader class, which here I'm going to call SCSP. So this is supposed to be kind of S, some sort of weird curly S. CSP is obviously a constraint satisfaction problem. And the idea is that we have this problem SCSP, which is parameterized by this set S. And S is the set of constraints. So this is the constraints that we're allowed to apply to our variables in the problem. So a constraint is just a Boolean function that acts on a constant number of bits. So it maps a constant number of bits to 0 or 1. So for example, we could have a constraint being function which takes 3 Boolean variables as input and does maybe A or B or not C. That's an example of a constraint that's satisfied if, for example, we have A1 and then B0 and C1 or something like this. Okay? And then an instance of the problem SCSP on n bits is specified by some sequence of constraints that are picked from this set S applied to subsets of these n bits. So if you have a constraint that depends on 3 variables, you apply it to some subset of 3 of the bits, which is some arbitrary subset of the bits. And the idea is when we're faced with an instance of this problem, of the SCSP problem, to determine whether there's some assignment to the variables such that all of the constraints are satisfied. So evaluate to 1 or true. We've already seen a couple of examples of this. So the 3-SAT problem is an example of SCSP, where S is the set of all disjunctions of Boolean variables or their negations on up to 3 variables. And the linear equations problem is the same, but where a constraint is satisfied if the equation is satisfied corresponding to those variables. And so we see that the complexity of this problem SCSP depends on the set S that we choose. We've already seen one example where it's NP complete, and another example where it's NP. Okay. And kind of remarkably, it's known that one or other of these cases is always true. So depending on S, this problem is always either NP complete or in the complexity class P. For some sets S, you can solve this efficiently. For other sets S, we think there's no efficient algorithm to solve it. And also, given S, we can determine which of these two cases is the right one. So we can determine whether the problem is likely to be hard or is actually easy. And this is a very early result. It's like 1978, sorry, by Schaefer. It's been improved in like a number of different directions since then, or at least people have thought about variants of this problem. For example, the complexity of the problem max CSP has also been completely characterized, where here we want to maximize the number of constraints that we can satisfy. Maybe we can't satisfy all the constraints, we want to maximize the number that we can satisfy. And this problem has also been completely characterized in a similar way. One example of this problem is which you may be familiar with, is max cut. So we want to maximize, so given a bunch of vertices and edges in forming a graph, we want to divide them into two subsets, one on either side of this so-called cut, such that we have the maximum number of edges across the cut. So that's an example of a maximum of a instance of max CSP. Okay, so there's this there are this sort of sequence of results that kind of characterize the complexity of these problems. And I should say that, at least for me, this is quite surprising and kind of beautiful, because in general, we don't have such a kind of precise classification of the complexity of problems when they come from some kind of quite interesting and wide class. For example, there's this famous theorem called Ladner's theorem, which says that assuming that P is not equal to NP, there's actually an infinite hierarchy of complexity classes between P and NP. So I think it's very beautiful that this quite broad class of constraint satisfaction problems can actually be completely characterized in this sense. Question?
Does it matter if you allow the constraints to be weighted?
For this maximization problem?
Yeah.
It's a good question. I think it doesn't matter. Actually,
if you allow exponentially varying weights?
It's a good question. I don't know, but I don't think it matters. I think, it's a good question. So I can't say for sure, but I don't think it matters. In fact, I have the book with me where they prove this, so I can tell you afterwards. Okay, so, but I mean, this is a good point, because it highlights the fact that making subtle changes to the definition of these problems can actually drastically affect their complexity. Okay, so that's this kind of body of classical literature. So now I want to talk about some related problems kind of in the quantum world. And we've already had a nice introduction to these in the last talk, so this is kind of lucky for me, because I'm going to be quite brief about them. So, at least about the introduction. And the natural quantum way of generalizing these classical constraint satisfaction problems is via this K local Hamiltonian problem, which, as I say, we've just heard about. And how do we define this problem? Well, basically, just to recap, I guess. So in a general setting, we imagine that we're given a K local Hamiltonian. So This is just a Hermitian matrix on the space of n qubits that can be decomposed as a sum of matrices hi, such that each matrix hi acts non-trivially on at most k qubits. So this is so H can be decomposed as a sum of things which are tensor products of some matrix acting on k qubits, tensored with the identity everywhere else. So that's a k-local Hamiltonian. And what we want to do is we want to find out what the ground state energy is of this Hamiltonian. We want to approximate the lowest eigenvalue of this matrix, basically. So just to be a little more formal, so we're given this matrix H described by this sequence of Hermitian matrices Hi, and the overall Hamiltonian is on like n qubits, say, and each of these matrices here Hi only acts non-trivially on at most k qubits, where we think of k as being very small, and we're given some kind of approximation bound, so some lower bound A and some upper bound B, such that there's some reasonably large gap between them. And we're promised that the ground state energy, the smallest eigenvalue of H, is either at most A or at least B, and we want to figure out which one of these is the case. So roughly speaking, we want to approximate the ground state energy up to some 1 over polynomial in the size of the problem precision. And in fact, there's some other kind of technicalities here which I'm just ignoring for this talk. Like basically, we have to assume that everything that we get in this problem is kind of reasonable. Like these matrices are specified in some sensible way. They don't have like ridiculously large parameters and things like this. But I'm just going to ignore these issues and say this is the problem that we're considering. Okay. So this is the k-local Hamiltonian problem, which probably many of you are very familiar with. And this has been much studied over the years, and we've indeed just heard about many results in this area. But going right back to the start, so we know that k-local Hamiltonian is a generalization of k max CSP. If you make the matrices Hi that occur in your decomposition of H, if you make these things into diagonal matrices that only have 0 or 1 on the diagonal, then this gives you precisely an instance of k max CSP. So this problem's at least NP hard to solve. But indeed, I guess maybe this should be like 99 or something. But indeed, it's been shown by Kitaev that things are worse than this, or maybe better than this, depending on whether you're an optimist or a pessimist. That in fact, it was shown like some time ago that 5 local Hamiltonian is QMA complete. So this is the k-local Hamiltonian, where we have at most 5 body interactions. And QMA is the quantum analog of the complexity class NP. So this is kind of even potentially much harder than NP to solve. So this was shown by Kitaev some time ago, and then later on this was actually improved to 2-qubit interactions by Kempei, Kitaev, and Regev in 2006. If you don't like that pun, you won't like much of the rest of the talk. I should warn you. This is a very nice result because, firstly, these 2-body kind of interactions are much more, I guess, physically reasonable, one could say, than kind of k-body interactions for k bigger than 2. And it's also nice because it kind of seems like the end of the line in terms of characterizing the complexity of these problems, because it's quite easy to see that one local Hamiltonian is in P. There's a polynomial time algorithm for it. Okay, so what else can we say about this problem? Well, there are a number of things we can say about it, and somehow a lot of the motivation for the more recent research in this area is applications to physics or connections to physics. In condensed matter physics, people tell me that one of the things that people really care about is calculating the ground state energies of real kind of physical systems, and this basically is an instance of k-local Hamiltonian. For example, a model which has been studied for a very long time is this Ising model, or Ising model if you prefer, which is basically the problem of finding the lowest eigenvalue of Hamiltonian that looks like this. So it's a sum over pairs of qubits of some weight times by z on the ith qubit tensor with z on the jth qubit. So here, yeah, I'm using this kind of condensed matter or physicsy type convention of having subscripts indicating the qubits on which operators are acting. And I'm going to think about kind of quite general cases usually. So there aren't really any restrictions on the topology with which things interact, with which qubits interact. So this I would call this kind of the general Ising model or Ising model, rather than just being on a line or something like this. But in any case, like this model has been studied for some time, and it's just an one example of many different interesting models in physics. And these connections kind of motivate you to think about K-local Hamiltonian with kind of restricted types of interactions. So somehow, if you have a Hamiltonian that's just of this form, then this seems much more restrictive than some kind of Hamiltonian where you're allowed arbitrary two-body terms at each for each pair of qubits. And this kind of really motivates us to try and understand what the complexity is of problems where you do have this restriction on the type of interactions that you're allowed, and maybe to try and prove like hardness or easiness of some of these other types of problem. Okay, and indeed, like people have been thinking about this kind of thing for some time. I'm only going to mention a couple of these results here, but like there are huge amounts of others in this area, some of which by people who are here. So, but the two examples which I'm going to mention are firstly a nice result of Norbert Schuck and Frank Strata from, I guess, 09, or maybe that's 08, I think 09. Anyway, who basically showed that Hamiltonians of this form are quite complex in that approximating the ground state energy for these Hamiltonians is QMA complete. So these are Hamiltonians where you have this Heisenberg interaction here, XX plus YY plus ZZ, occurring across the edges of some two-dimensional square lattice. And then you also have some kind of arbitrary local terms coming in as well, which can vary for the different sites in this lattice. So it's known that solving K-local Hamiltonian is still QMA complete for Hamiltonians of this form. Okay, and also sort of around the same time, Biamonte and Love showed that the problem remains QMA complete for Hamiltonians of these two forms. So here you have XX and ZZ interactions, or XZ and ZX interactions. And then these occur across pairs of qubits, and then there's also some kind of local terms coming in as well. And these are kind of very interesting results because these are more restrictive than the general case of two local Hamiltonians. So it's quite nice that they remain QMA complete. Okay. So these are cases, or two examples of cases, which are known to be hard, but there are some other cases which are believed to be a bit easier than this. In particular, Sergei Bravia and co-authors back in 2006 showed that K-local Hamiltonian is probably easier if the Hamiltonian is restricted to be so-called stochastic. So what this means is that a stochastic Hamiltonian has off-diagonal entries which are real and non-positive in the computational basis. So these Hamiltonians occur, in a number of places. So I'm told, and so that they're things which people have really been interested in, and because solving the K-local Hamiltonian for stochastic Hamiltonians is in the complexity class AM, which is Arthur Merlin proof systems. So this is a sort of classical complexity class where it's kind of like a couple of levels up from NP, if you like, in some sense. But in particular, it's in this classical kind of polynomial hierarchy. So this sort of infinite hierarchy of complexity classes, which is like, starts with P, and then you have NP, then you have things like NP with an NP oracle, and NP with NP with NP oracle, and so forth. But this class AM, which I guess I'm not really going to define formally, because it sits in this polynomial hierarchy, is considered to be unlikely that this problem is QMA complete. because it's believed that QMA is outside this hierarchy, though we don't have a proof yet. So this result is evidence that stochastic Hamiltonians are easier than general Hamiltonians. And this was even sharpened a bit later on by Sergei Bravi and Besson and Terhal as well, who showed that this problem can actually be completely characterized in terms of a complexity class, which is this class called stoch MA, so stoch is stochastic. And this is, again, a class which I'm not going to define, but it's a well-defined complexity class that sits between Merlin-Arthur complexity class and Arthur-Merlin. So it's a kind of fairly low down in like the world of complexity classes, and this problem seems to be unlikely to be QMA complete. So it's probably easier. Okay. So we've seen some examples of problems that are hard and some examples of problems that are easier. And what the problem I'm basically going to talk about today is a way of firstly generalizing this notion of SCSP to a quantum setting, and also kind of encapsulating some of these results. So this is a problem which I'm going to call S Hamiltonian. So here we're imagining that S is some subset of Hermitian matrices on at most k qubits for some constant k, where k might be 2, 3, something like this. And S Hamiltonian is just a special case of k-local Hamiltonian, where we're assuming that all of the matrices Hi that occur in our decomposition of our overall Hamiltonian H are all picked from S, with potentially some weights in front of them. So these matrices Hi that occur in our description of the problem, each of them is proportional to some matrix that's picked from this fixed set of constraints, if you like, this fixed set of interactions that we're allowed to apply. Okay, and then the general question I want to address is, given some set S, can we characterize what the complexity is of this S Hamiltonian problem? Is it in P? Is it QMA complete? Is it in stoch MA? All of these kind of questions. Can we characterize what the complexity of the problem is? Okay. So, are there any questions about that definition? Right. Well,
so from what you've said, it sort of seems like for each one, you can have it act on any subset. So you can't really put restraints on the sort of topology of the...
Yeah, in fact, I'll say a bit more about that in a minute, but that is a good point. Yeah, I am basically assuming that just as with the classical notion that you're allowed to apply these matrices across any subset of k of the qubits in your system. So this is quite a contrast to the previous talk, indeed. Okay, but it will turn out to be, well, I don't want to say essential, but it would turn out to be very useful for us to have this freedom. Okay, so we can see that some of these problems I've already mentioned fit quite nicely into this framework. So, for example, this Ising model. So here, again, there's this kind of general setting. You have these ZZ interactions across arbitrary pairs of qubits. So this for us is just the problem like ZZ Hamiltonian. So the set of interactions that we're allowed to apply is just Z tensor Z or ZZ, I could write. And it's been known for a long time that this is NP completes this problem. Okay, so this is one case down. So one way we can make this a little more complicated is by allowing arbitrary transverse magnetic fields in our Ising model. So this corresponds to adding local X terms with some arbitrary weights. So starting out with the same kind of Hamiltonian, and then also adding these X terms at wherever we want. Yeah.
Within each class, you can take the prefactor as arbitrary, right?
Yes.
No extra constraints can be positive or so, or not positive.
Yes, precisely. This again is an interesting question. Yes. So we're allowing arbitrary weights here. That they have to be real, but they can be positive, negative, 0. Yeah, all fine. Yeah. And again, there are reasonable questions one could ask about whether this is the right thing to do. But in any way, for us, the weights are arbitrary. Okay. Yeah, so this problem in our framework, we could say this is like ZZ, comma X Hamiltonian. So we're allowed to apply Z tensor Z, and we're allowed to apply X with arbitrary weights. Okay, and yeah, I'm just going to call this like transverse Ising model in future, so save me saying all these words. Okay, so that's a couple of examples. Then yes, another example is the Heisenberg model. I mean, again, this is a very sort of general setting where we have this Heisenberg interaction, XX plus YY plus ZZ, and we can apply it across arbitrary pairs of qubits in our overall system with arbitrary weights. So I guess this is like mixed sign or something like this. And for us, this is just like XX plus YY plus ZZ Hamiltonian. Okay, so this is something else people have thought about. And finally, another example that people have considered is this XY model, where now we're allowed to apply XX plus YY in any across any pair of qubits again. So all of these things, which have been studied in differing levels of different levels of detail, like these all fit into this general framework. And yeah, just to emphasize this point, like there's no kind of implied like spatial locality of the qubits. There's no kind of restriction on the type of interactions that you're allowed. You can have these pairwise interactions occurring across any pairs of qubits that you want. Okay, so yeah, so I mean, luckily the questions that have been asked already kind of have covered some of these remarks I wanted to make. So we're allowed to apply these interactions in the set S scaled by arbitrary real weights, which can be positive, negative, or 0. We're also assuming that we're allowed to apply these interactions across any choice of subsets of the qubits. So there's no kind of planarity or symmetry or anything going on there. We can do whatever we want. And finally, a subtle point maybe, like some of the interactions that are in our set S, they might not be symmetric under permuting the qubits on which the interactions act. And so we're going to assume that we can apply these interactions to any kind of permutation of the qubits. So if we have an interaction that's different, depending on whether we apply it across 1, 2 or 2, 1, we can apply it in both directions. That's allowed. And finally, we can always assume that the identity matrix I is contained within this set S, because what we care about is approximating the lowest eigenvalue up to some additive error precision. Like we can always, by adding the identity, this doesn't change anything to do with the complexity of the problem. So we can assume we have this for free. Okay. Right. So any questions about the problem so far? Great. Okay. So before I state the results, I first want to talk about a special case of this problem, which is quite a natural one to consider, which is a case where we assume that in our set S, we are allowed to have, for free, all one local terms. So you can say like we have X, Y, and Z in S to start with, or equivalently, we have all kind of single qubit Hermitian matrices because we can apply any of these with any weights we want. I'm going to sort of think about this as a separate problem called like S Hamiltonian with local terms, because it turns out it's quite a nice problem to study sort of separately, even though it's just a special case of the previous problem. And because we are allowing kind of these free extra local terms, the complexity of this problem must be at least as hard as the version where we don't have these terms for free, because any Hamiltonian we can produce without local terms, we can just still produce in this setting. So it can only make the problems harder somehow. And indeed, the results I already mentioned fit into this setting quite nicely. The result of Schuckenverstrate is that XX plus YY plus ZZ Hamiltonian with local terms is QMA complete. And the results of Biamonte and Lava that the same is true for S being XX and ZZ or XZ. Okay. So in our terminology, that's what these previous results are saying. Okay, and the first result of ours that I want to tell you about is an essentially complete characterization of the complexity of all other cases of this problem. So here we're assuming in this first result, this version with local terms, we're assuming that S is some fixed subset of permission matrices on at most k qubits for some constant k, some arbitrary but fixed constant k. So this is like k local Hamiltonian. Okay, and then we're going to characterize the complexity of different versions of S Hamiltonian with local terms. Okay, so how does the theorem look? Well, okay, so we're going to start out by looking at S prime, which is the set that we get by taking S and removing all one local terms from every element in S. So these are kind of irrelevant to the complexity of the problem because we're allowed to have them for free anyway in this setting, so they don't matter. So first we delete all of these terms from every element in S, and then we get rid of all like identity terms, if you like, these zero local matrices. So because again, they're irrelevant to the complexity of the problem. Okay, so then we have a number of cases that characterize the complexity. First, if the remaining set S prime is empty, there's nothing left, then S Hamiltonian with local terms is in P. So this is kind of the trivial case where everything in S originally was like one local, say. Otherwise, if there's some unitary U on one qubit, such that U, so quote, locally diagonalizes S prime, I'll define what that means in a sec, then S Hamiltonian with local terms is polynomial time equivalent to the transverse Ising model. So it's equivalent to this problem I just introduced. So yeah, I'll define what this means in a second. And then finally, if neither of these two cases is true, then the problem's QMA complete. So one or other of these three cases is always true. Okay, so one could say that this characterizes the complexity of S Hamiltonian with local terms. Okay, so I should define what goes on in this second case. So we basically we say that some unitary U locally diagonalizes some k qubit matrix M if U tensor k times by M times by U dagger tensor k is diagonal. So yes, it's just like a local notion of diagonalization. And we say that U diagonalizes the whole set S if it locally diagonalizes all matrices within S. So in particular, like, the point is that matrices in S might be of different sizes. One might be on 2 qubits, one might be on 3 qubits. But this notion kind of makes sense even in that setting. Okay, so we've seen that in this theorem that this case is polytime equivalent to this transverse Ising model. But you know, what's the complexity of this model? In fact, before I get into that, I should ask if there's any questions about the statement of the theorem first. Okay, so what's the complexity of this transverse Ising model? Because somehow, you know, we understand P and we understand QMA, but we don't necessarily understand what this problem's like. So firstly, it's at least NP hard because we can take the weights of these terms, of these X terms to be 0. So we get something that's just the Ising models. On the other hand, if we take any transverse Ising model Hamiltonian, it turns out we can change it so that it's a stochastic matrix. What we can do is we can apply local Z operations on each qubit such that the weight of that X term is positive, and this will map the weight to be negative. And this is sufficient to make all of the off-diagonal terms in this matrix non-positive, which means that this becomes stochastic, so the complexity of this problem is at most in stock MA. Okay? So, on the other hand, we don't know what the complexity of this problem is kind of more precisely than this. We just know that it's somewhere between NP and stock MA. So, as you know, all good complexity theorists do, when you don't know the complexity of something, you encapsulate it in a new complexity class. And in our case, because this is the transverse Ising model, we're unable to resist calling this complexity class Tim. So apologies to any Tims in the audience. Yeah, we couldn't think of any better name for this class than this. And for those of you who object to this kind of frivolous name, just think, you know, things could actually have been a lot worse. It also turns out there's no term in physics beginning with Y that was suitable there. So anyway, moving on. This theorem kind of completely characterizes the the complexity of this problem up to this fact that we don't precisely know what the complexity of this transverse Ising model is. Okay, so this is our first result. So are there any questions about that so far? Okay. So now our second result, which is in some sense a kind of generalization or strengthening of the first one, in other sense not, is only for two local interactions. So these are, this is the case where S is Hermitian matrices on at most 2 qubits. Okay, so in this case we have a slightly more complicated classification, but this is now for the S Hamiltonian problem rather than the S Hamiltonian problem with local fields, local terms. So okay, so firstly, if every matrix in S is one local, so only acts on 1 qubit, then S Hamiltonian is in P, so we can solve it efficiently. Otherwise, if there exists some unitary U such that U locally diagonalizes everything in S, then the problem's NP complete. So think of this as like the Ising model, if you like, if it's in this setting. Otherwise, if there's some U, this is this most technical case. Otherwise, if there's some U such that for all 2 qubit matrices in the set S, that U U tensor 2 diagonalizes the 2-body interaction part of that matrix HI. So in this case, we say, if there exists some U such that when you apply U tensor 2, when you conjugate HI by U tensor 2, it makes it into something which is proportional to Z tensor 2 plus some arbitrary kind of one-body, one-local terms. So it kind of diagonalizes the 2-body part of HI. So if there exists some U of this form, then the problem is TIM complete, if you like, similarly to before. So it's polynomial time equivalent to the transverse Ising model. Okay. And if none of these 3 cases is true, then the problem's QMA complete. So every S Hamiltonian problem fits into one of these categories. Okay, so this is the result. Okay, so let's look at some corollaries of this. So first, in particular, this general Heisenberg model is QMA complete because it fits into this 4th case here on the previous slide. And the same goes for the XY model, and many other cases as well. Like there's a number of natural cases one could write down, and using this theorem you can calculate what their complexity is. So we can think of this as like a quantum version of this theorem I mentioned right at the start by Schaefer, in that we somehow classify the complexity of this whole raft of different kind of quantum versions of constraint satisfaction problems in one characterization, which is not quite as precise, but nevertheless is kind of complete in some sense. Okay, so basically that's the statement of the results. In the last few minutes, I just want to talk a bit about the proof techniques. So are there any questions about the results so far? Okay, so let's talk about proof techniques. So we're going to use what's like the canonical way of proving these kind of dichotomy type theorems, which is basically to prove that some special cases are easy and that everything else is hard. You sort of carve out these cases which are easy to solve, and then somehow you have to show that everything else is difficult to solve. So there are many results in QMA completeness which are based around kind of explicitly encoding some quantum circuit or quantum Turing machine or something like this into a Hamiltonian using some kind of clock construction or something similar to this. And many of these results are very technical and beautiful. But here we're going to rely completely on, in some sense, a simpler idea, which is reductions from problems which are already known to be hard. So we're going to the hard part of our results is really proving kind of QMA completeness of a number of these different cases. And to do this, we're going to show that we can encode general Hamiltonians in these more sort of specific cases that we look at. And the first point is really to say that it seems like there's kind of a daunting array of different types of interaction we might have to look at, and there are many different, there are a huge number of different 2-qubit Hermitian matrices. And in order to simplify our task, the first thing we'd have to do is convert these into a normal form, which will kind of drastically simplify the problem. And this normal form goes back essentially the normal form that we're going to use goes back at least to kind of around 2001. It was invented by Dürr et al. And Bennett et al. I think some of the et al. Are in the audience. Basically, at least one special case that will be important for us is this case of symmetric interactions. So here we're imagining that H is some 2-qubit interaction, or Hermitian matrix on 2 qubits, which is symmetric under interchanging the qubits, and so it's unchanged if you swap the qubits over. Then what this lemma says is that there exists some U, it's a single qubit, unitary U, such that if you try diagonalizing H, if you try conjugating H by U tensor 2, then the 2 local part of what you get looks like XX plus YY plus ZZ with some weights in front. So this is quite nice because we've got rid of all of these other terms like XZ, ZY, all these kind of things that maybe make life a little more complicated, and we've just ended up with something that looks like this. Okay, so why is this kind of useful for us? Well, the basic idea is that if we have a Hamiltonian that's made up of 2 local interactions that are all kind of H interactions, so they're all kind of proportional to some matrix H, then if we conjugate each term in the overall Hamiltonian by U tensor 2, this doesn't change the overall eigenvalues of the Hamiltonian, because if we take H and we conjugate it by U tensor 2, this is kind of equivalent to taking U kind of outside this sum and just conjugating the whole thing by U tensor n. So we can apply these kind of local unitaries U for free, like in our problem. So this is why this kind of locality constraint is important for us. Okay, so this kind of lets us simplify things. Okay, and ultimately the basic idea is to say that if we want to prove that something's QMA hard, some A Hamiltonian is QMA hard, we want to approximately simulate some set of interactions B where B is QMA hard. B Hamiltonian is QMA hard. And if we can do this, if we can simulate B with A, then we've proven that A is hard. Okay, and the 2 kinds of reduction that we use are both based around perturbation theory, and they're both based around ideas that have been around for a while. In particular, we use kind of, if you like, first order perturbation theory, like 0th order, if you like, perturbation theory, and these gadgets kind of go back to about 2008 with Oliveira et al. And Shukla-Strate. And the basic idea is to say that at least this first kind of gadget that we use, the basic idea is to say that if we want to implement some interaction across qubits A and C, then we add some new qubit B between A and C, and we stick some kind of strong one local interaction on B, and this will somehow effectively implement some 2 local interaction between A and C. So just to see an example of the sort of result that we prove using this, there's if we consider this case XX plus gamma ZZ Hamiltonian, so we can show with local terms. So we can show that this is QMA complete by using like the following perturbative gadget. So we stick. So we want to implement some interaction between A and C. We stick this additional qubit B in, and we stick sort of XX plus gamma ZZ interactions across A and B, and also between B and C. And then we have this very strong kind of one local term here on B. And this kind of effectively forces qubit B to be in the state 0, because this is very strong here, this term. And then it turns out that you can show that up to some local terms and also lower order terms, you get an effective interaction between A and C that's proportional to something that looks like XX. So this has given you something new, which you didn't have before. Like previously, you just had XX and XX plus gamma ZZ, but now you've kind of effectively implemented XX. So you can use this indeed by die subtraction to make like XX and ZZ now. Okay. So that's one example. And then, so given that we can make XX and ZZ, this lets us use the result of Montanaro love to say that this case is QMA complete. Okay. And similarly, you can use the same idea for XX plus beta YY plus gamma ZZ for arbitrary beta and gamma, and also for this weird skew symmetric case XZ minus ZX, just based around the same gadgety ideas. And it turns out that I'm not going to go through the details, but this is in fact all of the cases that we need to complete this characterization of S Hamiltonian with local terms. Basically, the idea is we can use this normal form to put the Hamiltonians that we consider into a fairly restrictive kind of form, and then it means we only need to think about a few specific cases, and if we can prove they're hard, then we've proven that everything is hard. There are some kind of technicalities, but I won't bore you with them. And in particular, this is only the case for k equals 2, and to deal with k bigger than 2, you need to have different ideas. But again, I won't talk about those, and if people are interested, maybe ask at the end. Okay, so that's like the first result, that's S Hamiltonian with local terms. So I also want to talk a very little bit in the last few minutes about the case of S Hamiltonian where we don't have these free local terms coming in, because here the techniques are actually quite different for kind of interesting reasons. So yes, just to recap, this is the result that we prove. We have like over in P, NP complete, TIM complete, or QMA complete. And the most interesting cases really are the ones where we prove that they're QMA complete. So I'll just, okay, well maybe I'll just say this very briefly. So these cases 1 and 2 of this theorem are quite easy. Like in case 1, if you have something that's one local, you can compute the minimal eigenvalue just by looking at the individual terms. If you have something which is where every interaction is diagonal, then the minimal eigenvalues are achieved for some computational basis state. So this functions as a witness to put the problem in NP. Then you get NP completeness by showing that in fact you can produce any two-body diagonal interaction from Hamiltonians of this form. Okay, so case 3 basically turns out to be quite fairly straightforward to show that you can reduce this ZZ Hamiltonian with local terms problem to it, so it's complete for this new complexity class TIM. And the most interesting case is this case 4, like the QMA complete case. Okay, so the problem is that when we don't have access to these kind of arbitrary one local terms, then we don't have the same perturbative gadgets coming in. We can't use this trick of just sticking a new qubit in and adding like a strong interaction on that one qubit. So in fact, we have to use a different technique. And it's based on encoding the interactions that we want within some subspace. So we have some physical qubits, and within these physical qubits, we encode some logical qubits. And basically, this is going to be, the fundamental technique that we're going to use is related to this so-called projection lemma of a few years ago, Kempe, Kitaev, and Regev, which in our case, we're basing it on some results of Oliveira et al., which is that if we have two Hamiltonians, H and V, then if we form the Hamiltonian that looks like V plus some very strong multiple, a very large multiple of H, then the low energy part of the resulting Hamiltonian is effectively the same as projecting V onto the lowest energy eigenspace of H. So in fact, one can show this kind of rigorously, that the low energy part of the resulting Hamiltonian looks approximately like projecting the V onto the ground space of H. So this, if we can control this, then this lets us kind of change the interactions that we've got on offer to us. So like this case of the Heisenberg model XX, YY, ZZ sort of really shows the problems that we can have here, because this this interaction XX plus YY plus ZZ is invariant under conjugating it by any local unitary U. So this means that the same is true for the ground space of H, of the overall Hamiltonian, and in fact all of these different eigenspaces. So this means that if we want to implement some arbitrary Hamiltonian using only this interaction, then we're kind of out of luck. That we can't do something kind of arbitrary using only these interactions xx plus yy plus zz, we have to use some kind of encoding. Okay, so I'll just mention what the gadget is briefly, and then I think come to an end. So basically, we want to encode qubits within some kind of larger sort of set of physical qubits. And here, what we want to do is we want to encode some logical qubit within some physical qubits. So the gadget we're going to use is we're going to have 3 physical qubits, and within these, we're going to try and encode 1 logical qubit. So here's these 3 qubits, and then we have one qubit within them. And basically, I think I'll just, yeah, I mean, I'll just kind of mention this very briefly. The basic idea is to say that using some carefully chosen basis for these triples of qubits, we can produce some operators which look, by applying these interactions across different choices of qubits, we can produce interactions that look like Z and X. And then, okay, and then we still need to apply, we need to somehow make these kind of 2-body interactions. And it turns out that we can do this, but by applying, again, our interaction that we have access to across some interesting, some particularly carefully chosen choices of physical qubits. The only problem is we get some kind of unwanted extra term coming in here across these these logical qubits that we have, and we have to kill off this logical term somehow. But it turns out that we can do this too using some more perturbation theory. And as I'm out of time, I'll skip this, and you can always ask some questions afterwards. And basically, this was just one case where we've proven it QMA complete, but it turns out that similarly to the case with local terms, like we only need to think about a few special cases in the end, and that's sufficient to do everything. And we can come up with different gadgets that work for all of the different special cases that we need. And I should say that finding these gadgets actually turns out to be quite painful, and needed some computer algebra to do it. Okay, so this is really just the start of thinking about this problem, because even though we've characterized kind of all cases with like 2-body interactions of 2 qubits, we still have to solve the case where we have k-body interactions for k bigger than 2. So here's like a 3-qubit interaction. And also we need to solve the case where we don't have qubits, we have qubits for some d bigger than 2. And even classically, this is still an open problem. And there are many other interesting restrictions we could put on the problems that we consider, such as putting restrictions on the topology of how these qubits interact, on the weights of the interactions. And finally, we didn't kind of really resolve the complexity of this problem of the transverse Ising model. We just created a new complexity class for it. And our intuition is that we should maybe be able to resolve this, and at least this problem should be like Merlin-Arthur hard, so harder than NP probably. Okay, so this is basically everything I want to say. So thanks very much for your time. I'll just finish with an example of the final frontier for us, which would essentially be looking at qubit interactions on a regular lattice, which is a very interesting case which we have not resolved. So thanks very much for your time. Okay. So what we like to done now.
Questions?
To write to the previous talk, I mean, if you have arbitrary interactions, but they are kind of bounded in like operator norm, and then presumably the gadget trick becomes tricky. And so what can one do still? Like, what are the techniques?
It's a good question. Basically, again, this is something we didn't consider at all. Ultimately, we're always happy to have these kind of polynomial factors kind of coming in, and like. In terms of, I'm not sure I can even tell you what's known in terms of which problems are hard and which problems are easy if you only allow, sort of these things to have kind of constant norm and like. I mean, I guess, yeah. I mean, okay. I mean, because you want to be careful, because obviously you can like rescale everything by like 1 over poly, and then everything is bounded by 1, but then you have the gap becomes smaller.
Sure.
So in terms of like, if you have a constant gap and constant upper bound on how big the interactions are, I guess this would be like quantum PCP theorem or something like this to try and understand what the complexity is.
Okay.
of this. So yeah, I know very little about it. Maybe previous speaker does know more, but
Okay.
So how sensitive are the classes? Like, suppose I have a Hamiltonian that's in P. If I just move it slightly, a tad bit slightly,
It'll be
can I
QMA.
jump into? Right.
I'll say with very good confidence that, I mean, if you do any kind of sensible random perturbation of a Hamiltonian, you'll get QMA completeness. Like, but you have to be careful because you need to know what this random perturbation is in order to be able to do these constructions, right? So, like if you say, oh well, experimentally I just don't quite know what this thing is, then you won't be able to do the constructions that we have. So, I mean, what I can say is that almost all 2-qubit interactions will be QMA complete, but given something where you don't have kind of precise knowledge of it, maybe then it's you won't be able to say for sure if you like. So.
At first glance, your characterization in terms of the 2 local qubit case looks a lot like the classification of 2-qubit gates into entangling power and this
Yes, I mean
operator Schmidt norm stuff. Is that true?
Actually, this is a very interesting question because I don't think it's the same in terms of as in I don't think kind of on a formal level it kind of becomes the same kind of characterization in terms of like operator Schmidt decomposition or anything like that. But there's this kind of very interesting kind of general point, which is often it seems that if you have some interaction which is universal for quantum computation, like this goes hand in hand with QMA completeness of the finding the ground state energy. But as far as I understand, there isn't actually any formal result that kind of links these 2 things, and it would be kind of very interesting if one could actually find some formal link between these 2 things, because in particular this some of the interactions we look at, like this Heisenberg interaction, are known to be universal for quantum computation, but this, as far as we know, does not imply any any QMA hardness result. So I think it's a very nice question, and in fact I think given that, as I understand it, we still don't really know completely which sets of gates are universal, right? So then this is kind of maybe an interesting direction to go in to try and detect this problem.
One last question, maybe?
I have a small question, which is sort of a follow-up on Steve's, which is, so when you take these groups and classify them as QMA, it's sort of classifying all the instances or a worst-case instance of the problem. Has there been any delving into this idea that if you started in P, but then added some of these interaction terms very slowly, how quickly you enter, say, a hard instance of that QMA problem versus how long do I explore instances that I could still probably solve?
Yeah, so that isn't. But basically, I would say the interesting thing about our classification, if I go back to it, take a little time, is that basically, basically any epsilon perturbation of something easy by something hard will still be hard. Like as long as epsilon is like a constant, say, let's say, so it doesn't depend on the problem size, then you're going to get, well, okay, I should be maybe more precise, but I think hardness will come in immediately as soon as you have any little bit of hardness in your problem. But this is somehow just the framework that we're considering. It could be that for very special cases people care about, like maybe if there's kind of very small. So what we're thinking about somehow is just you're given the interactions and then you can apply them freely, like however you want with whatever weights. So in the case where you say, well, okay, maybe you're allowed to apply ZZ with a high weight and XX with only with a very low weight, then we don't know. Basically, that's another kind of interesting thing that we might try and solve. So.
Okay. Thanks again. Thanks.